Okay, in the last lecture we talked about maxima and minima, and we talked about critical points. And you find the critical points by finding, remember, three things. Any endpoints that are in the domain, any points where the derivative is 0, and any points where the derivative doesn't exist. Those are all critical points. And I said that if you want to find an absolute maximum or minimum, then you check at those critical points and you find out at which of those points is the function the greatest and which is it the least. Okay, now I need to point out to you though that there is a little bit of a catch there. Let me show you something here. Let's do this example. Sometimes, see, I have to remember to tell you this. If there is not an absolute maximum or a minimum, then you have to know that. So let's look at this. Let's look at f of x equals, let's just do x cubed plus x squared minus x plus 1. Okay, and let's go on the interval, because you know the domain of that is all real numbers, right? Okay, so, well, here, I'll tell you what, let's just leave it there. Let's leave it as the domain is all real numbers. Okay, let's say we're going to find the absolute max and the absolute min. So you first start by finding the critical numbers, right? Now, the domain here is all real numbers, so there's no endpoints on the domain. So then we need to look at where is the derivative 0 or where is the derivative non-existent. So let's write down the derivative. We have f prime of x equals 3x squared plus 2x minus 1. Okay, now that's a polynomial that is defined everywhere. So there's no places where the derivative doesn't exist. Okay, so there's no endpoints of the domain. There's no points where the derivative doesn't exist. So our only critical points are where is the derivative 0. So let's find those. We take the derivative, set it equal to 0, solve for x. Okay, I'm going to factor this. So we have 3x minus 1 is 0, or x plus 1 is 0. So that means x is a third. And also again at x equals -1. That's the two places where the derivative is 0. Okay, what if I wanted to start graphing this? So the derivative is 0 at 1/3 and again at -1. Let's find the actual points on the graph where that happens. So in other words, let's find the y values that go with those x values. So f of 1/3 equals, okay, and let's just plug in 1/3. Okay, that equals 27ths. Okay, so let's just say that's a little bit less than 1, right? So let's just say right here. So that's 1/3, comma, 22/27. Okay, let's plug in, what's the other critical number? -1. And that equals 2. So -1, 2. We'll just put it right about here. Okay, and so I know the derivative is 0 in those two places. So here's what I'm going to do. I'm going to draw just a horizontal little bit of a line there. And that represents the tangent line at those two places. Okay, now here's the thing that I didn't quite mention last time, and I need to point this out. If I asked you for the absolute maximum and absolute minimum, here's what you might say. You might say, well, these two have to be them, because those are the only critical points. And this one's higher, so it must be the absolute maximum. And this one's lower, so it must be the absolute minimum. Okay, here's the one thing to be careful about. The graph actually looks like this. And it actually has no absolute maximum or minimum, because it does get higher than that point and also lower than that point. So that's the part I need to point out that I didn't point out in the last lecture, is that this process I'm showing you here, that's how you find the absolute max and the absolute min, if there is one. Okay, you have to have some idea beforehand if there is an absolute max or an absolute min. Okay, and how would you know that? Well, that sort of stuff you know from your pre-calculus or college algebra classes. Okay, like for instance, this one is a polynomial of degree 3. So you should know from your pre-algebra or pre-calculus or college algebra class, you should know that a polynomial of degree 3 always looks like either this or this, and will not have a maximum or a minimum. Okay, now, just for the sake of argument, what if I said that we were going to limit the domain to, I'm going to just put here, f of x equals x cubed plus x squared minus x plus 1 on, let's say, the open interval from -2 to +1. Okay, so then the graph is being chopped down, okay, and it's only going to go from here to here. Okay, let's write down those points. This is -2, -1, and this is 1, 2. How do I know that? I'm just plugging in -2 into the function, and I'm plugging in 1 into the function. Okay, now those points on the ends are not critical points because they're not part of the domain, because I have parentheses here, and that's why I drew open circles. Okay, so they're not critical points because they're not part of the domain. So now what would you say about absolute maximum and absolute minimum? You would say there's no absolute minimum because the function keeps going down. Even though there's a limit to how far down it goes, it's still true that no matter where you are on the graph, you can always get a little bit lower. Okay? So there's no absolute minimum. But there is an absolute maximum because you've got that point there is a critical point and its height is 2. And over here, it never goes above 2. So in fact, 2 is the absolute highest level. So now you would say there's an absolute maximum of 2 at x equals -1. Okay? And finally, what if we did the same thing, but instead of parentheses around the interval, what if I put brackets? Then that means that these endpoints are now part of the graph. And so they are now critical points. And so now you would say there's an absolute minimum of -1 at x equals -2. And there's an absolute maximum of 2 at x equals -1 and at x equals +1. Okay? So you find the critical points. You find which critical point is the highest and which is the lowest. But you also have to ask yourself, does the graph go higher than that or lower than that? Okay? Now what I want to focus on today, though, are finding relative maximums and minimums, or local maximums and minimums. Okay? So here's what we're going to do. Let's start with a brand new problem here. But before I write the problem down, I want to introduce you to a couple of concepts. One is increasing versus decreasing, and the other is concave up versus concave down. Okay? So let's write this. Increasing, decreasing. This part is really just common sense. When I say it, it will make sense to you, I think. Okay? Remember, what does the derivative of a function tell you? The derivative tells you the rate of change. So, if the derivative is positive, that means that the change is positive, which means that the graph will be going up. Okay? So if f prime of x is greater than 0 for all x between, let's say, a and b, then f is increasing on the open interval from a to b. Okay, and if the derivative is negative, that means the change in the function is negative, which means the graph will be going down. So if f prime of x is less than 0 for all x between a and b, then f is decreasing on the open interval from a to b. Okay? Now, let me show you this thing called concavity. Concave up / concave down. Okay. So I'm going to start out writing and then I'm going to stop and do some explaining. So if f double prime of x is greater than 0 for all x between a and b, then, okay, so let's talk about that. So f double prime is the derivative of the derivative. So that is the rate of change of the rate of change. So if you think of the derivative as being velocity, then the second derivative would be analogous to the acceleration. And if the second derivative is positive, that tells you that the derivative is increasing. So the rate of change is increasing, which means that the graph will be curved upwards. The graph might be going down or up, but it will be curved upwards if the second derivative is positive. And when it's curved upwards, I mean looking like this. We call that concave up. So if f double prime of x is greater than 0 for all x between a and b, then f is concave up, on the open interval from a to b. Okay, and you can probably guess what happens if the second derivative is negative. If f double prime of x is negative for all x between a and b, then f is concave down on the open interval from a to b. So you can probably guess what that looks like. It's just the opposite of concave up, but let me explain it the same way I did for concave up. If the second derivative is negative, then that means the derivative is decreasing. So the rate of change of the function is decreasing, and that will cause the graph to be curved downwards. So it'll look like that. Okay? All right, now we're going to put these ideas to use. And we are going to find not just the not just the absolute maximum and minimum, but also any relative or local maximum and minimum for, let's do this function, cosine minus cosine squared. So let me write this down. I'm going to just write find all extrema of f of, in the textbook this is example 4, okay, on page, I don't know what page is this, 165. It says f of theta. Okay, I'm going to just use the variable x, so I'm going to write f of x. Okay, cosine of x minus cosine squared of x on the interval from 0 to 2 pi closed at the endpoints. Okay? All right, so let's find the critical numbers. So I immediately know two critical numbers, don't I? The endpoints of the domain, so 0 and 2 pi are critical numbers automatically. Okay, let's go ahead and find the first two derivatives. I want to look at both of them. I want to show you how the increasing decreasing works, and I also want to show you how concave up and concave down works. So we're going to need to look at f prime and f double prime. So let's go ahead and find both of them right now so that the busy work will be done out of our way. Okay, so let's find f prime. F prime of x equals, okay, the derivative of cosine's negative sine. And now here you have to be careful. We have minus. And we have to find the derivative of cosine squared. So you have the function cosine and you have the squaring function. The squaring function is happening to the cosine function. So we need to follow the chain rule. First you do the derivative of the squaring function. So we will get 2 cosine x, because why? Because you take that exponent down front and also you subtract 1 from it. Okay, then you say times the derivative of cosine, which is negative sine. Okay, so there's f prime. Let's just clean it up here because I know we can make it look nicer. So that equals negative sine of x plus 2 cosine x sine x, which is the same as saying sine x times negative 1 plus 2 cosine x, which this doesn't matter, but I just prefer this way. I'm going to write 2 cosine x minus 1 in those parentheses. Okay, so there's f prime. I'm going to erase my intermediate steps there. If you need to see them, again, you can rewind the video. Okay, I'm going to go ahead and get rid of that work and just keep the final answer. So there's f prime right underneath f. Okay, now let's find f double prime. That's the derivative of f prime. F prime is a product, so we'll use the product rule. So we have the derivative of sine, which is cosine, times 2 cosine x minus 1 plus sine times the derivative of this, which is 2 times negative sine, right? So in other words, negative 2 sine x. Okay, let's make that look nicer. So I'll go ahead and distribute this cosine. We will get 2 cosine squared x minus cosine x, and then I see also what else? Minus 2 sine squared x, which can be written like this: 2 times cosine squared x minus sine squared x minus cosine x. Now from your trig class or your pre-calculus class, you might recognize that this is cosine of 2x. So we have 2 cosine of 2x minus cosine of x. and that's f double prime. Okay, so I'm going to erase my work again. If you need to see it again, you can always rewind. Okay. And let's just take this guy and list it up there right underneath f prime. Okay, now what do we do with that information? Well, where did we leave off? We were starting to write down the critical numbers, and we said that there's a critical number at 0 and 2 pi because they are endpoints of the domain and they are part of the domain. Okay, where else do we find critical points? We take the derivative and you ask yourself, are there any places where the derivative does not exist? Okay. The domain of sine is all real numbers. The domain of cosine is all real numbers. So the domain of f prime is all real numbers. In other words, f prime exists everywhere. Okay. What's the third question you ask? Where is the derivative 0? Okay, so we write down the derivative. We set it equal to 0, and we solve for x. So sine of x times 2 cosine x minus 1 equals 0 means that sine of x equals 0, or 2 cosine x minus 1 equals 0, which is the same thing as saying cosine of x equals a half. Now remember, we're only told to work on the domain between 0 and 2 pi. So we just need to write down any numbers from 0 to 2 pi where the sine is 0 or the cosine is a half. So let's list those numbers. The sine is 0 at 0, and I already have that number written down. Where else is the sine 0? At 2 pi, I already have that written down. There's another place in between that where the sine is 0, and that is at the number pi. So let's write that down. Okay. Now, where is the cosine of x equal to a half? In a couple of places, right? One is pi over 3. And another one is 5 pi over 3. And this all boils down to whether you know your trig or not. Okay? So those are all the critical numbers. Let's relist those in order. If that's okay with you, I would just like to do that. Okay, so we will have 0, pi over 3, pi, 5 pi over 3, and 2 pi. There's our critical numbers. Okay, so let's find the critical points. All right, what do I get when I plug 0 into f? I suppose we're done with this this scratch work here. So what do we get when we plug 0 into f? F of 0 equals cosine of 0 minus the cosine of 0 squared. That equals 0, right? So we have a critical point at 0, 0. Let's plug in pi over 3. Okay, so we get cosine of pi over 3 minus cosine of pi over 3 squared, and that's a half minus a fourth, which equals a fourth. So we have a critical point at pi over 3, comma 1/4. All right, let's plug in pi. We get cosine of pi minus cosine of pi squared. That's going to be -2, right? So there's a critical point at pi -2. Okay, and then let's plug in 5 pi over 3. We get cosine of 5 pi over 3 minus cosine of 5 pi over 3 squared. That's a half minus a fourth, which is a fourth. And the last one is 2 pi. It's the last critical number. Cosine of 2 pi minus cosine of 2 pi squared is 0. Okay, so our last critical point is 2 pi comma 0. All right, so those are all the critical points. Okay, now here's what you do. The question is, which of those are maximums, which are minimums, and of those, which ones are relative and which ones are absolute? Okay? Now, there's two ways you can do this. And now that we have this written down, we don't really need the critical numbers anymore because they're written down right here anyways. Okay, so let's just clean this up a bit. Okay, now, there's two ways you can figure this out. One is using only the first derivative, and the other is using the second derivative. Okay, so I'm going to show you two different ways to do this problem of figuring out which of those are maxes, which are mins, which are absolute, and which are relative. Okay? So one way to do it, we call this the first derivative test. Okay, and it's only going to use f prime. And here's what we do. For one thing, I think before I do any work at all, I think let's go ahead and graph those 5 critical points. Okay. I guess since we're only going from 0 to 2 pi, I don't really need a negative x-axis, so let's do this instead. I'll just draw it by hand. I think it might be faster. Okay. All right. So we have one critical point at 0, 0. And then we have one at pi over 3, 1/4. So let's say that's pi over 3, and let's say 1/4 is this high. Okay, and then we have another one at pi -2. So if pi over 3 is there, then pi would be 3 times as far over. And I have a y value of -2. So that's going to be pretty low. Right about here, I would say. Okay, and then we have 5 pi over 3, 1/4. That's going to be right about here. And this high. And then 2 pi 0. So it's going to be way over here. And our point will be right there on the x-axis. Okay, so there's our 5 critical points. And you can guess already just by looking there, I hope you can figure this out, that there's going to be an absolute maximum which occurs in 2 places, and there's going to be an absolute minimum down there. And maybe you can figure out that these 2 endpoints must be relative minimums. But I'm going to show you how to actually work that out mathematically. Okay, so let's get to where we left off. This is the first derivative test. Here's what you do. Okay, we already have the first derivative. It's right here. What we can do is we can take any number between 0 and pi over 3 and plug it into the first derivative. Okay, so pick a number that you think will work out well and is somewhere between 0 and pi over 3. How about if I pick pi over 4? Okay, which is right about here. Okay, and I'm going to plug that into the first derivative. So what do I get? I get sine of pi over 4. What's the sine of pi over 4? It's root 2 over 2 times 2 times cosine of pi over 4, which is root 2 over 2, minus 1. Let's just work that out. And to be honest with you, I don't even care what the answer is. I just want to find out if it's positive or negative. Okay, so what's that going to equal? That's going to equal root 2 over 2 times square root of 2 minus 1. Okay, and the square root of 2 is bigger than 1. It's about 1.4. So this is positive, and it's being multiplied times a positive number, and so the product is positive, and that's all I care about. I'm just going to say that that is greater than 0. I'm not even going to bother figuring out exactly what it equals. Okay, so what that tells you is it tells you that the function is increasing between 0 and pi over 3. Okay, the function is increasing between 0 and pi over 3. Let's just take a green pen and let's just write that it's going up. Okay, and then we'll do the same thing for the next region between pi over 3 and pi. So pick any number you want between pi over 3 and pi. How about if we pick pi over 2, which is in there? Let's plug that into the derivative. So we get sine of pi over 2, which is 1, times 2 cosine of pi over 2, minus 1. What's that equal? That equals negative 1, doesn't it? Which is what? Negative. So the function is decreasing between pi over 3 and pi. So let's just put a green arrow going down. Okay. Then you go to the next region between pi and 5 pi over 3 and do the same thing. Let's see, let's pick a good number that makes sense here. Between pi and 5 pi over 3. And I think what would be the easiest number? I think actually, to be honest with you, isn't 3 pi over 2 in that area? Pretty sure it is. Because 3 pi over 2 is, of course, greater than pi. And it's also less than 5 pi over 3. So let's use that number. Okay, plug that into the derivative. And we get cosine of that number, which is 0, times, oh, I'm sorry, no, I'm supposed to write down the sine of that number, sorry. Sine of that number, which is -1, times 2 times the cosine, -1. That equals 1. Which is positive. So the function's increasing in this area. And now we have one more area between 5 pi over 3 and 2 pi. What would be a good number to pick there? I see that my scale is a little bit off. Let me just fix that scaling a little bit. 5 pi over 3 should really be much further over. Should really be way over here. Whoops, didn't mean to do that. Okay, 5 pi over 3 should really be way over here, so let's just fix that. And that blue point should have been right there. There we go. Okay, so between 5 pi over 3 and 2 pi. Pick a number that you like. You don't have to use the same ones I'm using. Pick some number that you like between 5 pi over 3 and 2 pi. A number that you know the sines and cosines of. I personally would pick 7 pi over 4. No, that's not going to work. That's not big enough. Let's see. Maybe it is. Let me think. 7 pi over 4. Yeah, that will work. That's just a little bit bigger than 5 pi over 3. Okay. And the sign of that number is -√2 over 2. And the cosine of that number is +√2 over 2. So let's see what we got here. We have -√2 over 2 times square root of 2 minus 1. Remember, I don't actually need the answer here. I just need to know if it's positive or negative. So square root of 2 minus 1 is positive, and then that's being multiplied times a negative. And so the outcome will be negative, which means the function's decreasing in this area. Okay, so let's go ahead and write down what we just found out about the function, where it's decreasing and where it's increasing, okay? So I'm going to write f is ... okay, and then we will write increasing on the interval from 0 to pi over 3. It's decreasing on the interval from pi over 3 to pi. And then it's increasing on the interval from pi to 5 pi over 3. And then it is decreasing on the interval from 5 pi over 3 to 2 pi. Okay? So what that allows us to say is that allows us to say now with very much confidence that that's a relative minimum because the function is going up after that, and there's nothing on the left. And on the right, the function's going up, which means that is a low point right there. It allows us to say that this is a relative maximum because the function is going up and then it's hitting that point, and then the function is going down after that. So this is a high point. So that's a relative maximum. Okay, and then I can say that this is a relative minimum because the function is going down and then it hits this point, and then after that the function is going up. So this is a low point. And finally, oh no, there's two more. We know that this is a relative maximum because the function's going up and then hitting that point and then going down, which means this is a high point. And finally, we can say that this is a relative minimum because the function's going down to that point and then it stops. So that's a low point. Okay? That's how you use the first derivative to find when the function's increasing and decreasing. And then you could figure out from that which critical points are relative maximums and which are relative minimums. Okay? But I want to show you also how you could go even further. Let's do what's called the second derivative test. This tells you when the function is concave up or concave down. Personally, I think this one's a little bit easier. It requires you to find the second derivative, so that takes a little bit of work. But here's what I think is way nicer about this. We are not going to have to plug in numbers between the critical points. Instead, all we're going to do is plug in the critical points. I find that easier. So the first critical number was 0. Let's plug that into the second derivative. You get 2 times cosine of 0 minus cosine of 0, and that equals 1, which is positive which tells us that the function is concave up. Let's indicate that with gray. We'll just do this, okay? Now let's plug in the next critical number, which is pi over 3. Okay, f double prime of pi over 3. We get 2 times cosine of 2 pi over 3, which is negative 1/2, minus cosine of pi over 3, which is 1/2. So what's that going to equal? Again, I don't really care. I just care if it's positive or negative. But since this one's pretty easy, I'll go ahead and write it down. That's negative 3/2. But the important thing is that that's negative. So I know that the graph is concave down here. Okay. Let's go to the next critical number, which was pi. Plug that into the second derivative. We get 2 times cosine of 2 pi minus cosine of pi, and that equals 2 plus 1, which is 3, which is positive. So the graph is concave up at that place. All right, go to the next critical number, which was 5 pi over 3. Okay, plug that into the second derivative. We have 2 times the cosine of 10 pi over 3. Okay, I have to think about that one for a second. That is negative 1/2. You got to know your trig if you're going to do well in calculus. And then minus cosine of 5 pi over 3, which is positive 1/2. And that's going to be negative 3/2 again, which is negative. So the function's cosine down here. And don't just guess and say, well, it was cosine up last time, it must be, concave, I should be saying. Don't just say, well, it was concave up last time, so it must be concave down this time, because it keeps flipping back and forth. It doesn't have to flip back and forth. It could be concave up 2 times in a row. Not this function, but functions can do that. So you need to actually do the work to check, okay? All right, and the last critical point is 2 pi. 2 times cosine of 4 pi minus cosine of 2 pi. That's 2 minus 1, which is 1, which is positive. So the function's concave up here. Okay, so let's go ahead and write this down. F is ... we can say concave up at, I'm not going to write an interval here, I'm going to write the point. Well, here, let's do it like this. Let's just write at x equals 0. Okay, it is concave down at x equals pi over 3. It is concave up at x equals pi. It is concave down at x equals 5 pi over 3. It's concave down in other places too. I'm just saying these are the 5 places where I've checked. Okay, and it's concave up at x equals 2 pi. And why did I check these 5 points? Because these are the critical points. Okay, now using that, you can draw a pretty decent graph of what f must look like. Watch how I do this and listen very carefully. I'm going to start here at the beginning, and I'm going to go here to the end, and I'm going to pay attention to whether the function should be going up or down, and also the curvature. Okay, so when I leave the starting point, I should be going up and curving up. So something like this. And at some point in between here, I should start curving down, but still going up. Going up and curving down. So you get kind of an S shape. And then after I leave that point, I should be going down and curving down. And my goal is to get to here. And I need to be going down and curving down. So it's going to go something like this. And at some point along the way, I'm going to keep going down, but start curving up. So at some point along the way, it's going to go like this. And that point where the concavity changes is called a point of inflection. When the concavity changes, there was another one right around there somewhere. Okay. All right, now let's continue on drawing the graph here. I'm going to leave that point at the bottom, and I'm still curving up, and I'm starting to increase. And my next checkpoint is to check in right there. So I need to keep going up. At some point, though, it starts curving down. So at some point, it stops curving up and starts curving down. Going up, but curving down. So you see there's another point of inflection somewhere around there. Okay, and then the last part, I'm still curving down, and now I'm going down. And then at some point I need to start curving up. So there's another point of inflection somewhere around there. We're not finding the points of inflection right here. We'll practice that in the next lecture. Okay, and there you go. I'll erase all these extra marks here, and you'll see that we are left with a fairly decent sketch of the graph of our function. Okay? That's a heck of a lot better than if I had just went like this. That'd be very choppy. So, first derivative test tells you where the function's increasing and decreasing. Second derivative test tells you where the function's concave up and concave down. If you just wanted to know where are the relative maximums and minimums, you would not technically have to do both of those. You could do either one. You could use the first derivative and say, well, it's increasing and then decreasing, so right in the middle where it changes from going up to going down, that must be a relative maximum. Okay, or you could use the second derivative test and say, well, here's a critical point and it's concave down, so that's a relative maximum. Okay, so let's draw arrows pointing to the relative maximums. Well, let's not draw arrows, let's write them down. Okay, relative, or local if you prefer that word, maxima occur at, and let's write down the points where those happen. There's one at pi over 3, comma 1/4. And there's another one at 5 pi over 3, comma 1/4. There's relative minima at what points? There's one at 0, 0, and another one at pi negative 2, and another one at 2 pi 0. Okay, now let's find the absolute maximum and minimum. The absolute maximum occurs at two places, which is pi over 3, comma 1/4, and again at 5 pi over 3, comma 1/4. And what's the absolute maximum value? It's 1/4. And the absolute, or some people call it global, minimum occurs at only one place, which is pi, comma negative 2. And what is the absolute minimum value? It's negative 2. Okay, that was a very long problem, very detailed. We're getting more and more into detailed stuff, and hopefully you saw from this that if you're going to be successful here, you have to know your calculus. All right, we're going to practice this some more in the next lecture, but that's all for today.